Okay, this is 6.6, modeling with trigonometric functions. So there's nothing new per se in today's lesson. There's no new theories or concepts. We're just taking what we've learned now and we're applying them to some real world problems. So the first one is about Cape Capstan in New Brunswick. There's a change in depth of the water in the harbor. So on one day in October, the tides have a high point of approximately 10 meters at 2 p.m. and a low point of approximately 1.2 meters at 8:15 p.m. A particular sailboat has a draft of 2 meters. This means that it can only move in the water that is at least 2 meters deep. The captain of a sailboat plans to exit the harbor at 6:30 p.m. So that's all the information we're given. And then we're asked, can the captain exit the harbor safely in the sailboat at 2 p.m.? So in other words, it's asking us, will the height of the water be greater than 2 meters, right, at 2 p.m. if his draft is 2 meters? Okay, that's, sorry, at 6:30 p.m. Yeah, thanks. So water height greater than 2 meters at 6:30 p.m. Yeah. Question? Okay. So that's what the question's asking us. So we want to take all this information they've told us now and create a sinusoidal, not just a sinusoidal graph or curve with it, but we want to create an algebraic equation, right? Because when we have an algebraic equation, then we can just plug in the time and figure out what the height is, right? So we'll start off by graphing because it helps us give a visual, right? Create a sinusoidal function to model the problem and use it to determine whether the sailboat can exit the harbor safely at 6 p.m. I think it should be 6:30.
Oh, it's really weird.
Okay. So here's the information we're given. We're given the fact that it goes as high as 10 meters at 2 p.m. So we decided to start this particular graph at noon. Doesn't matter, as we'll show later, where you decide to put your y-axis. Okay, your translation would just change correspondingly. Okay, we could have put this at midnight and gotten 12 hours more this way, but we don't have any data all the way until 2 p.m. so it makes sense to start it at noon. Okay, so that's why we chose 0 to be at noon, and 2 p.m. would be 2 units over, and we know it's at a max height of 10 meters. So we put that there. Next, we know that it goes to a minimum of 1.2, which is over here, all the way over here at 8:15 p.m. Okay, so we can draw that, and we make that assumption that it's a smooth curve in between those 2 points. Any questions so far? All right, so once we have this, now we can start to make some calculations about our variables. So we know we're trying to get to a graph that has a final formula that looks like this. So we just need to solve now for these variables, A, K, D, and C. And believe it or not, we already have enough information in this problem to solve for all these variables. So let's start off. The first one is A. We find that by taking the max value and the minimum value and subtracting them, and then dividing by 2. That'll give us the distance from the equation of axis to the top or the bottom, otherwise known as the amplitude. Okay, so there is 4.4. 10 minus 1.2 is 4.4. Next, we calculate our period. Remember, period is always dictated by this formula. Doesn't matter what units you're in, doesn't matter whether you're graphing time, whether you're graphing dimensions, or just straight units, you're always going to start off with this formula. Period equals 2 pi over k. And the reason for that is that that's from the actual sinusoidal curve. The fact that a normal sinusoidal curve takes 2 pi to go through its whole period, that's where this comes from, okay? So the next, we know that the period is actually 12.5. How do we know this? Anybody know? Why do we know the period is 12.5? Here's all we have so far. How do we know the period is 12.5? Here's my standard y equals sine x. from my high point to my low point. This is always half of my period. Okay? And we can figure that out by putting in units here. This is pi, this is 2 pi. So we're going here from pi over 2 to 3 pi over 2. So this distance from the high point to the low point is always going to be 1/2 my period. Okay? So for all sinusoidal functions, if you have the high point and you have the low point, you're going to multiply that by 2 and you have the period. Okay, does that make sense? Right? Assuming that this curve is consistent or constant, that's going to be half your period. So we just need to take that time length then between the high point and the low point. So we'll go back here. The high point occurs here at 2 p.m. and the low point here occurs at 8:15 p.m. So that's 6 hours and 15 minutes, or 6.25 hours. We're going to multiply that by 2 and we get 12.5 hours for a period. Any questions there? All right. So that's why we know period right here is 12.5. Once we know that, we can solve for k. So we cross multiply here. K is 4 pi over 25. Next, we want to solve for c. C is just as easy as the amplitude. If you have the maximum and minimum, rather than subtracting it, you add them and divide by 2. That's finding the middle, right? The middle axis. So we're finding this value here. Okay? And that's 5.6. So now we have all of our variables. We can plug them in. The last one to solve for is d. Okay, it's always the last one. It's the last one when we go from the equation to the graph. It's the last one when we go from the graph to the equation. Okay, how can we find out the value of d? It's the amount at which we translate this curve. So we could use a cosine or a sine function here. Which one would you guys want to use?
Cosine.
Why? Yeah, it's closer, right? If we use cosine, we just have to move this graph how much to the right? 2. If we use cosine, we would have to move it all the way from here, which is all the way back here. Okay, we'd have to kind of extrapolate and move it this way. I think it ends up being like 17. Not hard, we can figure that out, but it's much easier to see that the cosine is just 2 over. Yeah.
If we started the graph at 2 p.m., there would be no translation, right? We could do that.
Exactly. Yes, very good point. And we actually talk about that in a second at the end. Good question, though. Okay. So we translate it 2 units over to the right, so it becomes negative here. And then we add in all our other variables. So there's our k value, there's our c value, and there's our a value. So there's our final equation. Any questions? Okay. So now we want to know what the height is at 6:30. So we plug in the value of 6.5 here for t, and we calculate the height. It's 2.8 meters. So it's safe for the boat to leave. Any questions? Okay. So reflecting here, what characteristics of your model would change if you use sine function to model the problem? The variable d would change. So in other words, the horizontal translation. What role did the maximum value play in determining the required horizontal translation? It showed us how much to move it, right? It was 2 over, right? So showed us how much to translate, and it also, in a way, its location, I'm going to say, encouraged us to use cosine. Right? The max value is really close to the y-axis, so we chose cosine. If t equals 0, so this was Alex's question, was set to 2 p.m. instead of noon, how would the equation change? Would this make a difference to your final answer? So the equation definitely would change because there would be no translation here. The d value would be 0. If we set our y-axis, if we put our y-axis right here, we would have had a perfect cosine function already. So we wouldn't have had any translation. Any idea why would that not have changed our answer? Yeah.
Well, I was gonna say because then the period changed, but it doesn't.
No, yeah, it doesn't change.
It could be if you use the other way, it's still giving the same answer for 2 p.m.
Why?
Because if you could leave at 2 p.m., it doesn't matter which way you would use. It's safe for him to leave either way.
No, it would be a different equation, so we would get a different answer, right? You see? No, but like think about it. Our equation here now, our final equation here would not have this 2. So if we go ahead and plug in 6.5, we're going to get a different answer. So why don't we get a different answer? There's obviously a flaw in my sentence. If we plug in 6.5, we'll get a different answer.
Yeah.
So in other words, what I'm asking, why would we not plug in 6.5? What would we plug in for time? If we put the axis here, guys, what are we going to put in for time here? It's kind of confusing, right? But what would we put in? We couldn't put in 6.5 anymore because remember, those are the units from the y-axis. As much as we like to think of them as time, and we're stuck in this stereotype that 6:30 has to be 6.5,
So it's 4.
it would be 4.5 now, right? You guys understand that?
Yeah.
Yeah, so we wouldn't plug in 6.5. Good. We would plug in 4.5 here. This value would be 4.5. If axis is at 2 p.m. Okay? That's why it's important to be aware of the axis values that you're choosing and where those x values line up. Okay, any other questions about that? All right. That was a really good question though, because when you make this, you make this graph, it makes a lot of sense the way it's done. But before it's created, you don't know what you're doing really, where you're putting the axis. So it's important to think about those things and how they relate to the actual equation. Okay, that's where kind of the conceptual understanding really matters. You're not just creating an equation and plugging in values. Number 2. The following table shows the average monthly means of the daily 24-hour temperatures in Hamilton, Ontario. Each month's average temperature is represented by the day in the middle of the month. So, we have all these days of the year. There's 356. We have the days measured out from January 1st on the x-axis out, and then we have the temperatures listed here. Okay? This column is not really useful to us. We don't really care what month. This day you can figure out is in September, right? Okay. It says plot the temperature data for Hamilton and fit a sinusoidal curve to the points. So we're just taking each one of these points, plotting them out, and we fit a curve. Easy enough. Estimate the average daily temperature in Hamilton on the 200th day of the year. Sorry, before we do that, I should have actually read here. Should have asked us to do that as well. Create an algebraic model of the curve. So we want to create an equation now that represents this curve. And we have enough information, right? We have the max, we have the min, which is all we really had in the last curve. And we can go ahead and do that. So we find our A value by taking our maximum minus our minimum. So our maximum up here is 21.9 minus our minimum, which is negative 4.8. Remember, negative minus a negative becomes a positive. So we get our A value of 13.34. Our C value is done in a similar fashion. We're just adding the max and min. Our period is 2 pi over k. We know that there's 365 days in a year, so this is going to repeat after 365. So that's our period value. And then we solve for our k value. So this is 365 here. There's our k value. Now we have all of our variables except for the last one, which is d. So we plug them all in, and we use a sine function this time, and use the equation of the axis, which is here, at 8.55. You need that to find out, if you're going to use your sinusoidal function, you need to put that line in to find out where it actually passes through the middle. Okay, that's very important. Okay, you need that line because now you can draw that line down and figure out where it passes through the middle of the curve, and that'll be how much you need to translate, which is here at 116. You guys see that, where that number comes from? So I've moved it to the right, 116, so I'm going to minus 116. Very important that you put that line in so you can dictate. If you're just guessing here, you're not going to be accurate. You figure out that line first, draw it in, and then draw it down. That's how much you need to move it over.
To be accurate, the C, that's 116, right?
This?
Yeah, by looking at that, you wouldn't say that's 116 for sure.
It's pretty accurate actually, because I think they go by 20. So so they're going 1, 2, 3, 4. Yeah, so they're going by 25s. So that line there is pretty close. Maybe you might guess 120, but you could always choose a higher resolution, right? If you're graphing it yourself, right?
So what if it's on a test?
You get 0.
So I thought you didn't like it, you had to guess.
Okay. B. Estimate the average daily temperature in Hamilton on the 200th day of the year. So we go to the day 200 here and we guess the value.
Oh.
Yeah, I said that on purpose. We don't guess. We take 200, we plug it into our algebraic equation, which we've created, and we get 21.8. No guessing. Any questions there? Now we could have chose a cosine curve, and if you didn't like where this process of guessing this location, you could have said that a cosine curve looks a lot closer to almost exactly at 200. See that? So you could have used cosine and had this translation minus 200 instead. Okay? All right. Last example. We're looking at a sinusoidal curve again. We're talking about the population of owls versus the population of mice. It says the population size O of owls, which are the predators in a certain region, can be modeled by this function. We're given the function, and T represents the time in months, and T equals 0 represents January. The population size of M is the mice prey is given by this function. So we're given these two functions now. So in my mind, half of our work is done. We can graph these and start to answer the questions. Sketch the graphs of these functions. So this is a straightforward process. This is our equation of our axis. It's 1,000 is 20,000. So there's 1,000 right here. There's 20,000. This is our amplitude, 100. So we go up 100 to 110, down to 900. This is our amplitude, 4,000. We go up to 24,000 and down accordingly. Compare the graphs and discuss the relationship between the two populations. Oh, sorry, and the last one we can do is we can figure out our period. Again, our period is equal to 2 pi over k. our k value is given in both scenarios. Okay, it's pi over 12. So we can solve for the period, which in both cases works out to 24 months. Okay, that might have been the only difficult part of developing that graph. Okay, once we do that, it's asked us to compare the graphs. So we have them overlaid here very nicely. So these are the exact graphs on the previous page. Notice the little cuts here in the y-axis. That's so that we can, get a better look at the function itself rather than unnecessarily graphing all that empty space. Okay, everyone's familiar with how to do this? Yeah, okay. You cannot put a function across squiggly lines, okay? Because everything obviously gets distorted if you're jumping values, okay? So you can't make a plot here and then something below the line here and just kind of connect them with a line. No, it won't work that way. Okay, so you have to make sure that if you're going to put these lines in, it has to be all empty space. All right, so we're comparing the graphs here. What do we notice when the owl population is at its highest? Okay, the owls are really eating well here, and the population of the mice start to diminish. Okay, because there's so many owls eating them. Now the mice get so low to a point where there's no more food for the owls, so the owls' population starts to diminish. So we have this relationship where the owls are eating the mice. As they eat too many, their population goes down because there's not enough mice to eat. And as their population goes down, the mice thrive and their population goes up. So you can see the mice population is always just a little bit ahead of the owl population. The relationship, what's happening. Mice population is more, the owl population starts to increase. Okay, so there's always this kind of like cat and mouse relationship, or owl and mouse relationship, where one is rising as one is lowering. All right, how does the mice to owls ratio change over time? So here we can make a table of time. So here's our months. And then we just list the mice population during those months and the owl population, and we figure out a mice to owl ratio. So taking the mice population and dividing it by the owl, and we can create a time versus mice to owl ratio. Right? This is a graph of time versus how many mice there are in comparison to owls. Okay, there's 24 times the mice as there are to owls in January. In June, there's 18.5 the number of, or 18.2 the number of mice to the number of owls. Okay, in December, there's the least amount of mice to the number of owls. So there's only 16 mice for one owl. Okay, so what they find then is that this relationship of time and mice-owl ratio is also sinusoidal. Okay, so we can actually develop and create an equation for that relationship as well. Okay, and why we might want to do that is if we're predicting patterns based on mice-to-owl ratio. We're basically taking these two graphs and we're combining them into one sinusoidal curve. Okay? Does that make sense to you guys? All right, last one. When is there the most food per owl? When is the safest for the mice? So this is pretty straightforward. The most food per owl occurs when the ratio of mice to owls is the highest. There are more mice per owl. Obviously, there's the most food when there's all mice around. The safest time for the mice occurs at the same time when the ratio of mice to owls is the highest. There are fewer owls per mouse. This occurs near the end of the 21st month in the 2-year cycle. So at this point, right here, it's the safest for the mice, and it's the most plentiful for the owls. There's a lot of mice, they're safe in numbers, and the owls are digging in. That's why their population is rising. Okay? I don't know why this is funny. All right. In summary, the graphs of y equals sin x and cos x can model periodic phenomena when they are transformed to fit a given situation. The transform functions are of the form this and this, where A is the amplitude, K is the number of cycles, and 2 pi, when the period is 2 pi over K. D is horizontal and C is vertical. This is all review. Tables of values, graphs, and equations of sine and cosine functions can be used as mathematical models when solving problems. Determining the equation of appropriate sine or cosine function from the data or graph provides the most efficient strategy. However, since accurate calculations can be made using the equation. Any questions?